long element. Oh, we're good. Okay, last time we were talking about the long elements of a finite Coxeter group, which we denoted by W naught. And we said it has some nice properties, like it's an involution. And if you multiply on the left by W naught, that gives you an anti-automorphism of the Bruhat order. Similarly, if you multiply on the left, and then also if you conjugate by W naught, that's an automorphism of the Bruhat order. And so one thing I was saying at the end was the set of elements covering the identity element in the Bruhat order is just a set of simple reflections. So, since conjugating by W naught gives an automorphism of the Bruhat order, this should mean that it will just permute the simple reflections. So the map that sends a simple reflection S to W naught S W naught. And again, I could write an inverse here, but it doesn't matter because W naught is its own inverse. So this map is, well, I could say it's a bijection from S to itself, but actually it has more properties. It's an automorphism of the Coxeter graph of our Coxeter system. And again, this just means that it preserves adjacencies and also like the labels of the edges. So let me give some examples of this. So if we look at the symmetric group Sn, so the Coxeter graph looks like this. It's just a path with S1, S2, S3, S4, it goes up to Sn minus 1. And this map basically just flips this path around, so it just sort of reflects the path through a vertical line. So if I take W naught, Si, W naught, this is S sub n minus I. And this is something you can just check directly because we know what these permutations are. Like W naught is just the decreasing permutation, and so you can check that this is what this does. Another example. Let's look at Bn, the hyperoctahedral group. So here, it looks like this. So here's S0, S1, S2, S3 up to Sn minus 1, and there's a label 4. And, well, okay, I guess let's assume that n is at least 3. Then, yeah, so let me actually do that. Then there are no automorphisms of this graph other than just the identity. So that actually is the map. So in this case, W naught, Si, W naught is just Si. And I'll do one other example. So let's take Dn. Maybe I want to assume n is at least, well, I probably want to assume n is at least 4, maybe. Maybe 3 is fine, I don't know. But, okay, so remember here, the Coxeter graph looks like this. So this is S0, S1, S2, S3, S4, and so on up to Sn minus 1. And in this case, okay, it's a little bit weirder. It depends on the parity of n. So first of all, in any case, W naught SI, W naught will be SI whenever I is between 2 and n minus 1. So in other words, it's going to always, this automorphism will always fix this part. But then it could either swap S0 and S1 or just keep them fixed. And this is what ends up depending on the parity. So W naught S0, W naught is S0 if n is even. And it's S1 if n is odd. And similarly, W naught S1 W naught is S1 if n is even, and it's S0 if n is odd. So actually, okay, let's see what happens for n equals 3. For n equals 3, this actually just is the same as S4, right? Because I don't have this, so it really is just a path. And in that case, I actually do swap them, which is what happens when n is odd. So I think this, I don't need to assume n is at least 4, let's assume n is at least 3. But again, if n is equal to 3, then this is actually just this. Except here the n is 4. Okay. Good up to there? Okay. So if you have any automorphism, okay, so here's an interesting sentence. Every automorphism and okay, there are more interesting sentences than this, but it's somewhat good. Of the Coxeter graph yields an automorphism of the Coxeter group and an automorphism of Bruhat order. On W. Okay, so I'm using the word automorphism in 3 different ways in this sentence, but I mean in general, if you have just like some type of mathematical structure, then an automorphism should just be a bijection from that object to itself, preserving the structure that you care about. So here I'm saying an automorphism of the Coxeter graph as like an edge-labeled graph. This gives you an automorphism of W as a group, so group automorphism, and it gives you an automorphism of the Bruhat order, which is a post-set automorphism. Okay. And let me state a theorem, which I don't remember if they prove this in the book, maybe they don't, but I'm not going to prove it. Okay, so the theorem is, suppose Ws is irreducible and the number of simple reflections is at least 3, then if phi from W to W is an automorphism of Bruhat order, and it fixes all the simple reflections. So phi of s is s for all s and s. Then either, so it's either going to be the identity map or the map that just takes everything to its inverse. So either phi of x is x for all x in W, or phi of x is x inverse for all x in W. Any questions up to here? Yes?
You said when you have an automorphism of the Coxeter graph, it preserves adjacencies and something else.
Oh, the edge labels. Yeah, so like, for example, here, you can just see that there's no automorphism of this labeled graph because, like, as a graph, if I ignore the label, I could flip it around like I did here, but I want to preserve the label 4. So that forces me to fix it. Okay, so let's talk about parabolic subgroups and quotients. Okay, so if I have some set J of simple reflections, I'm going to let W sub J be the subgroup generated by those simple reflections. So be the subgroup of W generated by J. So then this is called, okay, well, so this is called a parabolic subgroup. So there's a bit of a clash of terminology in the literature, which is that some people use the word parabolic subgroup to refer to this. Some other people will say that this is what's called a standard parabolic subgroup. And so the notation here, or the terminology, is that a standard parabolic subgroup would be something like this, and then a parabolic subgroup is anything conjugate to a standard parabolic subgroup. For now, I think I'm just going to say parabolic subgroup for this thing, but just know that, like, in general, parabolic subgroup could mean something conjugate to one of these things. Okay, so here's a proposition. I think I will not prove it, but it's good. So first of all, if I take my parabolic subgroup Wj with the set of generators J, this is a Coxeter system. Here, I'll do a bulleted list. So the second thing is, for all elements W in the parabolic subgroup, if I look at the length of W viewed as an element of this Coxeter system, and I'll write that as L sub J, then this is equal to just the length in the original Coxeter system. Actually, okay, I think this is easy to see. This is basically saying that, well, first of all, if I have a reduced word of length for W of length L sub j of W, then that is a word representing it in the bigger Coxeter system. So that would show that this is greater than or equal to this. But to get the reverse inequality, you say, well, if I have some word representing W just over J, then it should contain a reduced word in the big Coxeter system because of the deletion property. I don't know if that made so much sense, but okay, basically the reason why this is true is because if I have some word representing W that only uses letters from J, then actually it contains a reduced word, and by reduced I mean in the big Coxeter system, that only uses letters for J, and this is because I can delete things using the deletion property to get down to a reduced word. Okay. Okay, these I think are not too hard. So W sub I intersect W sub J. If I had two subsets I and J, well, this is just going to be the parabolic subgroup generated by I intersect J. And if I take Wi union Wj, and then I look at the subgroup generated by this. So like when I take the union, that might not be a subgroup, but if I take the subgroup generated by the union, this will be the same as the parabolic subgroup generated by I union J. And finally, if Wi and Wj are equal, well, that's if and only if I and J are equal. Okay, so one other thing is that, well, if Wj, if this subgroup is finite, then we know that any finite Coxeter group has a long element. So we can talk about its long element. Okay, so if Wj is finite, it has a long element which we will denote by W naught of J. Right, I guess the point is that we might want to talk about the long element of the entire group, which I'll call W naught, and then if I want to talk about the long element of this parabolic subgroup, that'll be W naught of J. So let's write D subscript I superscript J for the set of elements of my Coxeter group whose right descent set is contained in J and contains I. So remember, the right descent set is the set of simple reflections such that if you multiply W on the right, the length goes down. So then I'll also write W superscript J for D sub empty set S minus J. Okay, in other words, this is the set of elements of my Coxeter group that do not have any right descents in J. So all of their right descents are in the complement of J. And I guess we can also write d sub I for dii. So d sub I is just the set of things whose right descent set is exactly equal to I. Okay, so here's a proposition. So every element little w in my Coxeter group has a unique factorization as what I'll call w superscript j and then times w sub j with w superscript j in capital W superscript j and W sub j in big W sub j. Okay, so this is saying I can factor my element uniquely as something that doesn't have any of its right descents in J times something in the parabolic subgroup generated by J. And moreover, this factorization is what's called length additive, which just means that the length of W is the length of W superscript j plus the length of W sub j. So let me do an example. Let's say W is the symmetric group S9. And let's let J be 1, 2, 4, and 7. Okay, so in this case, W, let's take W to be...
Colin.
Yes?
Is that S1, S2, S4, S7? Then when you say 1, 2, 3,
Oh, yes, sorry. Yes, I totally should have done that. I guess I'm identifying, it's often common to identify the numbers with the indices of the simples, but yeah, you're right. S1, S2, S4, S7. Yeah, thank you. Okay, so then let's take W to be this permutation. 4, 2, 6, 9, 1, 5, 7, 8, 3. So, okay, in this case, what I have written down is that W superscript j is 2, 4, 6, 1, 9, 5, 7, 8, 3. So I'll try to make sense of this in a second, but first let me just write it. And W sub j is 2, 1, 3, 5, 4. 6, 7, 8, 9. Okay, so what's happening here is that J So the simple reflections in J, basically the S1 and the S2 allow you to permute the first three numbers. The S4 allows you to swap the fourth number and the fifth number, like if you were to multiply on the right by these. And the S7 allows you to swap the seventh and the eighth numbers. So what I can do here, if I want to, basically the way that I get this is I put the first three numbers into increasing order. And I put, because of the S4, I look at the, let me see, what am I doing? Oh, yes, the fourth and the fifth. So, okay, these three numbers are the things that I can permute using S1 and S2. These two numbers are the things that I can permute using S4. And then using S7, I could permute the numbers in positions 7 and 8. And I want to find my W superscript J so that none of its right descents are in this set. And so in order to do that, I basically just have to put these numbers within each of these blocks into increasing order to get rid of the descents in those positions. So I put this in increasing order to get 2, 4, 6. I put that in increasing order to get 1, 9. The 5 stayed the same. 7, 8 was already in increasing order, and then the 3 stays the same. And then for the W subscript J, that's basically the thing that I had to multiply by in order to do this rearranging into increasing order for each block. Okay. And you can check that this is, in this parabolic subgroup. Does this make sense? Okay, so here's a corollary of this proposition. So every coset of the form some element times this parabolic subgroup has a unique representative of minimum length and in fact it is this thing. And it is W superscript J. So these minimum length coset representatives are just the elements of big W superscript J. Actually, maybe I'll break this corollary into two corollaries, just because I want to justify this. So proof. Well, basically, the point is that if two elements belong to the same coset, so let's say I have, if U times Wj is W times Wj, then I claim that U superscript j will be equal to W superscript j. And the reason is just, well, okay, what does this mean? This just means that I can write W as U times some element of this parabolic subgroup. So I can write, okay, W is, let's say, UV for some V in this parabolic subgroup. So we can, according to this proposition, write U as U superscript J, U subscript J, and similarly for W. And then, well, W, again, I can write it as this. But I can also write it as UV, and U can be written like this, so it's U superscript J, U subscript J times V. But the point is that V is in my parabolic subgroup, and this element U sub J is in the parabolic subgroup by the definition here of what W or what U sub J actually means. So here I've written W as some element of W superscript J times some element of W sub J. And the proposition says that this factorization is unique. So in fact, W superscript J must have been equal to U superscript J. By the uniqueness in the proposition. Okay. And okay, so I guess the reason that it's minimum length is because, well, if I had something that was not already this element W superscript J, this thing, then I could factor it as W superscript J times some other thing, and the length of that element would be bigger than the length of W superscript J. So the reason that the minimum length here is showing up is just because of the length additivity. Okay, does that make sense? Okay. Let's see. I can probably fit the other corollary there. Or I could just go over to the other board. Okay. So the other corollary is similar. If let me see. So if my parabolic subgroup is finite, then this coset has a unique element of maximum length, and I can say what it is. So it is just W superscript J times this long element of the parabolic subgroup, so W naught of J. And these maximum length parabolic, or sorry, these maximum length coset representatives are exactly the elements of this set DJS. In other words, the elements of the group whose right descent sets contain J. Okay. Oh, okay, here's an example. Let's take, again, W is S9. J is the same set as before. S1, S2, S4, S7. W will be the same permutation 4, 2, 6, 9, 1, 5, 7, 8, 3. So in this case, W naught of J, so the long element of this parabolic subgroup, well, basically, I should try to put everything that I can in decreasing order. I sort of have these blocks that I'm allowed to permute, and I just put everything that I can in decreasing order there. So this should be 3, 2, 1, and then 5, 4. So here I put this in decreasing order, this in decreasing order, and then 6, I can put the 8, 7 in decreasing order, and then 9. And the reason that it has to be like this block has to be the smallest numbers, and then this is the next smallest numbers, and then there's the 6, and then the 8 and the 7, and then the 9. The reason that like the numbers within the blocks, or they're increasing among the blocks, is just because like if you have these elements and you start with the identity, then the most you can do is permute these 3 numbers, but you can't move them out of these positions. And similarly for the 5 and the 4 and the 8 and the 7. So all you can do is just that. And then also, in this case, this W superscript J times W naught of J. So this would be the maximal element of this coset, or maximum length element. This ends up being, if you just multiply it, 6, 4, 2, 9, 1, 5, 8, 7, 3. And I mean, that's just because we computed W superscript J, and we computed W naught of J, and we multiplied them. Or, okay, another way of thinking of this is just what I get by putting these numbers in decreasing order, and then putting these numbers in decreasing order, and then putting these numbers in decreasing order. So I start with my original permutation and just put things that I can into decreasing order. Okay? So I'll just mention that we've been dealing with right descent sets, but there are left analogs of these, so I'll just say there are mirrored versions. Of these things. So we write, okay, this is kind of annoying to tech, sorry, Elliot, unless you have a good way of doing it. There's like a command you can use, but so it's superscript J, W is the set of W in W such that the left descent set of W is contained in the complement of J. Okay, so it's exactly like W superscript J, except it's for the left descent set instead of the right. So this is the set of minimum length coset representatives of the right coset. So right cosets of the parabolic subgroup. And every W in W can be factored uniquely as W equals, so W sub j times, okay, so let me explain this in a second, times superscript j W with W sub j in the parabolic subgroup and superscript j W in superscript j capital W, but this is not the same W sub j as before necessarily. So not the same W sub j as before. Okay, and the way we get this is just by taking inverses. So I'll just say get this from all of the previous results by using the fact that if I take the set of inverses of elements of my parabolic subgroup, that's just the parabolic subgroup, right? A subgroup is closed under taking inverses. And if I take the set of inverses of elements of W superscript j, such that W is in this, that is just superscript j capital W. So maybe I should say that this set of minimum length coset representatives is called a parabolic quotient. So here we have the parabolic subgroup and the parabolic quotient. I guess superscript j W is also called a parabolic quotient, but I guess you just have to, it depends on whether you're dealing with left or right, and some papers use one convention, other papers use a different convention, but yeah. Okay. Let's see, how much longer is chapter, is what I'm doing? Okay, not that much. So we can restrict the Bruhat order to this parabolic quotient to get some coset. Get some interesting coset. So let's define this projection map. Pj from W to W superscript j by just sending each element little w to this W superscript j that I had before. So this is the minimum length representative of the coset W times Wj. Okay, so here's a proposition. This map is order preserving for the Bruhat order. And all this means is that U is less than or equal to V if and only if Pj of U is less than or equal to Pj of V. And a corollary of this is that any two elements of this parabolic quotient have an upper bound under the Bruhat order. Well, it's an upper bound in the Bruhat order, like on the parabolic quotient. And the reason for this, let's see, did I write down the proof? Oh, I guess I did. It's not hard though. Okay, so the proof of the corollary, that is that, well, we know already that any two elements of the Coxeter group have an upper bound in the Bruhat order. So let's let U and V be in the parabolic quotient. So we can find some W in the whole Coxeter group with U less than or equal to W and V less than or equal to W. But then U is the same as Pj of U, right? Because U is already in this parabolic quotient, so you can think of Pj, the letter P is for projection. You can think of it as like projecting to the parabolic quotient. But if you're already in the parabolic quotient, this just does nothing. And, well, this is less than or equal to Pj of W because U is less than or equal to W, and the projection is order preserving. But then similarly, you can say the same thing for V. So that means that Pj of W is an upper bound for U and V within the parabolic quotient. And I guess I'll also just mention so if the parabolic quotient is finite, then it has a maximal element under the Bruhat order, which you could call W naught superscript J. Or in fact, it actually is like what you get by taking the long element W naught and projecting. So it is like this W naught superscript J. And again, this is just, well, any two elements have an upper bound, and so there's a maximal element because it's finite. Okay. Let's see if we can get to lattices. I want to talk about lattices because I mentioned them on the next P set. So hopefully we can get there, but I want to finish this first. So, okay, proposition. Suppose W is finite. And J is some subset of S. Then we have this map, alpha, from W superscript j to W superscript j, defined by so alpha of x will be W naught times x times W naught of j. So here this is the long element of W, and W naught of j is the long element of the parabolic subgroup. So this is an automorphism. An anti-automorphism. Okay. Of Bruhat order on the parabolic quotient. Okay, and then I think the last thing I'll just mention, so I'm sort of just stating things about, like I'm not going through the proofs of this, but I'll just state one more thing, which is that this chain property is also true in the parabolic quotient, which means that we have, actually this post-it is graded, so theorem, this is the chain property but for parabolic quotients. So if u is less than w in the parabolic quotient, then there exists x naught, x1, dot, 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 xk in the parabolic quotient with u equals x naught less than x1, less than dot, 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 less than xk. This is w. And the length goes up by 1 at each step of this chain. Yes?
So when you wrote that anti-automorphism,
Yeah.
that first W0 is the longest word in W,
Yes.
and then the second is the longest word in WJ.
Yes.
Okay.
Did you like how I had an automorphism and I changed it to anti?
Yeah.
Okay, yeah. I was happy about that. I mean, it's not grammatical anymore, but like, I'm okay with that. Okay. So a corollary of this is that the Bruhat order on the parabolic quotient is graded.
Oh, so it's even if WJ is not finite?
Oh, I think, yeah, even if it's not finite, it should still be graded. Although, yeah, I think it doesn't require finiteness. Yeah. Okay, any questions up to here? Okay, let's talk about lattices. So, I had this history of lattice theory that my collaborator wrote out, which was pretty amusing, but I forgot to write it down. Maybe I'll do that next time. But okay, anyway. Yes, there's this area called lattice theory where people study lattices. So let me tell you what a lattice is. What?
Not lattices.
Not lattices, yes. Yeah, some people pronounce it lattices, but that is wrong. Yeah, maybe this is actually a good thing to mention. Like if you have a word that ends in like X, like matrix or vertex, then the plural is like e's, like matrices, vertices. But if you have a word like lattice, the plural is just lattices, not lattices. So, yeah. Okay, anyway. So let P be a poset. Then if we have some elements x, y, and z, we will say that z is the greatest lower bound for x and y if, and this is not necessarily always going to exist, but if it does exist, it's the greatest lower bound of x and y, and if z is the unique maximal element of the set of things that are, well, lower bounds for x and y. So the set of, I don't know, u in P such that u is less than or equal to x and u is less than or equal to y. So again, this doesn't always, like this set of lower bounds isn't always going to be, well, it's not always going to have a unique maximal element, but if it does, then that's called the greatest lower bound for x and y. And similarly, let me say, this is also called the meat. So this is also called the meat of x and y. So then there's also a dual notion of least upper bound, which is also called the join. So the least upper bound, also called join, is defined dually. So it would be the unique minimal element of the set of upper bounds for x and y. Okay, so here's a definition. A lattice is a poset L such that any two elements have a meet and a join. So such that any two elements x and y in L have a meet, and the meet is denoted by this wedge symbol. So x meet y. This is the greatest lower bound of x and y. And they have to have a join which is denoted with this V symbol, X, V, Y. Okay? So I'll give some examples of lattices, but I'll just say that I guess one reason lattices are nice is because you can view them as poset or order theoretic object. Yes, Catherine?
How do you remember what the symbols correspond?
Okay, yeah, how do you remember? Let me do the Boolean lattice and then I'll explain where, how you remember. The way that I remember is I've done it a lot and I just remember. But yeah, this is a point of contention among anyone who first sees lattices. Okay, but let me just say first of all that one reason, or one way that you can view lattices as like order theoretic objects, like posets, where you're defining these in terms of like upper bounds and lower bounds. But you can also think of them as like algebraic objects because really these are operations. So there's, the meet and the join are actually operations where you can take two elements and like combine them in some way. So this is in some ways some algebraic object. But I think for the most part, I'm going to view them as like order theoretic objects, but there are also some people who look at them algebraically. Okay. So here's an example. Let's do the Boolean lattice. Well, okay. Maybe I'll first answer Catherine's question in one way. So like, here's the picture. Here's X, here's Y, and their meet should be some lower bound. It's like the greatest lower bound of them. So this here would be X meet Y. And you can see that the symbol we use is exactly what you would not want it to be based on what this picture looks like. And similarly, the join is like up here, X join Y. So one way you could remember it is it's the opposite of what you would want if you look at this picture. Okay, but the other way you can remember it, which I think is probably the reason that these symbols are used, maybe, is coming from the Boolean lattice. So remember, we defined this before. These are just, okay, so the Boolean lattice is the collection of subsets of, let's say, bracket n, ordered by containment. This is a lattice. And in this lattice, so the elements, remember, are subsets of the numbers from 1 to n. And if you want to take the meet of two subsets, so this is like the biggest thing that is a subset of, say, x and a subset of y, well, that's just the intersection. So here, if I take x meet y, so again, x and y are subsets of the numbers from 1 to n. Their meet will just be their intersection. And so this, you can see the meet symbol kind of looks like a pointy version of the intersection, which is maybe a better way of remembering this. And similarly, the join is the union. Okay. Okay, so here's another example that I haven't said before. You can look at the set of divisors of some positive integer ordered by divisibility. So, example, the divisors of some positive integer n under divisibility is a lattice. So here's an example, let's say with n equals 12. So I have 12 at the top, and then I would have, let's say, 6 here, and I want to take 4. Okay, it should look something like this. So it should be 1, 2, and 3. Yeah. So these are the divisors of 12, and 2 is a divisor of 6, which is why 2 is less than 6 in this coset. Similarly, 3 is a divisor of 12, but like 4 is not a divisor of 6, and 6 is not a divisor of 4, which is why they are incomparable. And the reason this is a lattice is because, oh, well, okay, maybe I should ask, why is this a lattice? Like, what is the meat? Yes, Yinsa?
Just take GCD and LCD.
Yeah, GCD and LCM. Right, so here, the meat of x and y is just their greatest common divisor. And their join is just their least common multiple. Maybe I should draw something that's not a lattice.
Oh, Colin.
Yes.
Also, the Boolean lattice is just a special case of divisor.
Of what?
Of divisor.
Oh, that's a really good point. Yeah, yes. The Boolean lattice is the lattice, this divisibility lattice for a particular. Okay, so how would you realize it this way?
Just
How
like
would you?
product of n primes.
Yeah, so if you take a product of n distinct primes, then the lattice of divisors of capital N will be isomorphic to the capital N, if capital N is a product of little n distinct primes, then the little nth Boolean lattice is isomorphic to the lattice of divisors of capital N, right? Yeah, that's a good point. And, okay, so here's an example of something that's not a lattice. I mean, it's easy to draw something that's not a lattice, but here's one way. This is not a lattice. For example, if I took x and y to be, say, these two elements, they don't have a join because, well, they have two upper bounds, this one and this one, but they don't have a least upper bound. And so here x and y would have a meet, so that's fine. But just saying that there are two elements that don't have a join, that automatically makes it not a lattice. But there are other things you could say here. You could say, well, these two elements here don't have a meet, for example. But anyway, yeah, so this is not a lattice. So let me define a special type of lattice. And I want to do this just because it's mentioned in the P set that I'll release today. So a lattice L is called distributive if the meet operation distributes over the join and the join operation distributes over the meet. So if we always have x meet y join z equals x meet y join x meet z. And x join y meet z equals x join y meet x join z for all x, y, and z in the lattice. So the Boolean lattice is distributive. And this is just because, I mean, we know what the meet and the join are. They're like intersection and union, and you can check that, I mean, this is sort of just a basic fact about sets and set theory, that the intersection distributes over union and union distributes over intersection. And also the divisor lattice will be distributive. So you can check again that like GCD distributes over LCM and LCM distributes over GCD.